lower column densities. We have a couple more steps to go, and then we can start applying it to aspects of the intergalactic medium. In the meantime, I put together, it's kind of big, a very simple website that you can use. I guess there's the link up top to access, I think, all the materials that I've used so far. And there may be some updates to them as I go, but nevertheless, here you got. And again, if you want a full Dropbox of it, it's hundreds of megabytes now with all the figures. You can email me and I'll add you to the viewing of the Dropbox. But it should be, most of the material will be here on this simple website. Got that? Okay. I can give you the link later if you didn't get a chance to write it down. So we had generated, or I had shown kind of the modern results on the bin evaluation of this frequency distribution, f of n, which describes the incidence of absorption lines through the Lyman-alpha force as a function of column density and principal Doppler parameter, which we haven't talked about yet, and also as a function of redshift, which I'll get to in a few minutes, but still focusing on column density. These are the bin evaluations from high-quality shell data from both Keck and the VLT. What we need to do next is to model this frequency distribution. And we're motivated to do that to reduce the bin evaluations, which do seem to have a pretty well-behaved, appear to be rather well-behaved, to a few parameters, in part so that we can use this frequency distribution to do calculations. It'd be more or less impossible just using the bin evaluations. And it also simplifies our exploration in terms of redshift. A challenge here is that there is no physical model for the frequency distribution. As I said at the start, it's an empirical approach, not a physical one, really. And so we have freedom to really choose whatever model of interest, really, and by and large, we're just guided by the data. I showed you a couple lectures ago the estimations from the early work. It was well described by a single power law. F of n goes like n to some beta power. But as time has gone on and the data has gotten better, and as we've extended the distribution function to a wider range of column densities, we've gone to broken power laws, broken disjoint power laws, the sum of several functional forms, and then I've landed on Hermite Gaussian spline functions that are monotonic over the distribution function. And I'll show you that ugly form probably at the end of tomorrow's lectures. Anyways, as I said, the increasing complexity really reveals the increasing quality of the data as well as the larger range of column densities that we apply it to. One could do simple, one couldn't, and some still do, simple chi-squared fitting of the models to the bin evaluations that I showed you. I remind you the best estimate of the uncertainty is just a Poisson estimation, which for large lines is a Gaussian anyways. But a proper treatment really is to take the observations, squeeze that down, and perform likelihood analysis, maximum likelihood analysis. I won't go through all the equations here, but it's nice to visualize the concept in part because I think it can be applied to many areas of astrophysics. If I have the chalk. Did you take the chalk, Mark? Visualize the distribution space, and here I'm just going to focus on the column densities as a series of cells. Chop them over the cells. Okay, each with some width, which I'll describe as a delta column density. Right. We have measured a set of absorption lines with individual column densities. You can ask, what's the expected mean number of absorption lines that should be in each cell? And that will be equal to this frequency distribution, which we're after in our modeling, times the size of the cell, which is its width in the column density regime, times the survey path, which I introduced last time. So again, depends on how many quasars are in our survey, and we use to get the number of absorption lines that we actually observed. Fine. And then we assume that the absorption lines are distributed randomly, so if there is clustering, and there is, but we'll ignore that for now. which means that the probability of detecting M lines, given that mean value is just a Poisson process, u to the m power over m factorial e of negative mu. Okay. And we now have our ability to generate a likelihood because we can take the product of all those probabilities over, let's say there's m, big M cells describing our distribution. Okay. So break up the volume into a series of cells. Use the fact that the mean number in each cell should be proportional to our frequency distribution, and the fact that we have a Poisson process under the assumption the absorption lines are uncorrelated, and you wind up with a simple description of the likelihood function. Fair enough. One then performs what looks somewhat to be a swindle, maybe not quite, but let now the size of the cells, that delta NH, goes to be small enough that each cell has at most one absorption line within it. Okay, so let delta N go towards 0 to the stage where you have at most one absorption line within it, or one system, or one galaxy. As I said, this technique here can be applied to many domains of observational astronomy. At that point, then, my probabilities takes on just one of two values, e to the minus mu if you have 0 lines within that cell, or mu times e to the minus u for one cell. And I will skip through the math that is in the notes, but that allows you to reduce this likelihood function, skipping, to a pretty simple and straightforward equation to evaluate. This is now the log likelihood function. It's just the integral over the frequency of the frequency distribution over my survey volume. And then, so that's just the model on the left-hand side. It doesn't speak at all to the data. And the right-hand side is the frequency distribution evaluated at each of the absorption lines detected in the survey. Simple enough. So with that, you can calculate the likelihood for any functional form you wish to introduce for the distribution function, and maximize the likelihood on the parameters that describe that model to recover the best description of the data. Best in the statistical sense here. Not necessarily a good model. I'll show in the next lecture how we assess the model quality, but it's certainly the best in terms of the model you've adopted. And so with that in mind, fitting the data to at these lower column density range, we call of the Lyman-alpha forest, the best fit power law from this data set gives you a beta of about 1.65. The Kim et al. Data, which I showed in comparison to these, you get a slightly shallower slope, although they also fit to a slightly higher column density. That's a number to take away in terms of the distribution of gas here in the IGM. A power law distribution is a pretty good description over this quite a few orders of magnitude in the column density, with a power, an exponent of order minus 1.5 to minus 1.6. Good. That's the column density distribution. As I said, starting off with this frequency distribution, we separate the B values. We have separated out the B value distribution. Let me now bring it back in. That same line profile analysis that I showed you this morning does give you unique B value for each of the absorption features modeled. Here's a scatter plot from just one sight line, column density on the x-axis, and B value measured on the y-axis. I would ignore the data down here. It's in a regime where I wouldn't trust the measurements, but here in the bulk of the data is certainly fine. And while it looks like there may be quite a strong evolution with B column density, appreciate there are many more lines here, which leads to the larger peak-to-peak scatter that your eyeball picks up. To zeroth order, there's very little dependence on the B value distribution with the column density, which has been our incoming assumption. There may be a floor, if you will, in the smallest B value detected at a given column density, but that's not especially important here. Just binning up that data set, you get a bin evaluation which looks something like this. And unlike the frequency distribution, where you had more or less your freedom to choose a distribution function, there are physically motivated, there's a physical motivation for the Doppler parameter distribution. I show it here without derivation because it's painfully messy. But under the concept of an optical depth, fluctuating optical depth field, which I'll come to in a few minutes, the distribution function you would expect is something like this, e to the minus b over b to the fourth, all divided by b to the fifth. Pretty funny looking distribution, but indeed it is a good description of the observations. Here shown with a b sigma of the order of 26 kilometers per second. So we have now a distribution function for the Doppler parameters, a distribution function for the column densities, and we can just take the product of the two to get the full distribution function. The mean of this functional form, given the 26.3 kilometers per second, is 30 kilometers per second. So maybe another number to walk away with today is that the average broadening of the absorption features within the Lyman-alpha force is of the order 30 kilometers per second, and obviously with a large tail out to about 100. This functional form has within it a sharp cutoff. You can see it right here, right, just in the plot of the distribution. And you identify a lower limit to the Doppler parameters on the order of 20 kilometers per second, and might then ask what is setting that lower limit to the widths of the absorption features. I'll remind you that the Doppler parameter is defined as such. The square root of a thermal broadening term plus any turbulent motion that one has within the gas. And it's reasonable, at least, to assert that at the very lowest bounds, what you may be seeing is a limit to the broadening imposed by the fact that the IgM has a finite temperature. And you may even go so far as to associate that 18 kilometers per second with the temperature of the IgM. I'll return to that on Friday, but that's not a bad first order assumption or approximation. And to let you know, for a Doppler parameter 13 kilometers per second, you'd get 10 to the 4 Kelvin. So the implied temperature for something like 18 kilometers per second would be a few times 10 to the 4 Kelvin. Actually a bit higher, indeed a little bit too high. And we'll understand why that's the case on Friday. There's also an upper bound, if you will, to the measurements at least of the broadening. What that's due to, I think, is an open question. It could even just be a simple, again, another aspect of the approach that we've taken to decomposing lines into individual features. Line blending, the fact that you have multiple lines very close to each other will, for example, make it difficult to measure a very low broad component within the data. But it may also well be something physical in the IgM. Okay. I think I'm done with the shape of the frequency distribution, column density, and Doppler parameter. The last bit is the normalization with density. And that's described as the line density. And in painful but true, in the literature, this takes on many notations. Can't even really... Well, I can kind of tell you why, but I don't like it. DNDZ, N of Z, N of Z, and L of Z. They all stand for the same thing. I'm sorry, but it's true. I've tried to use this one as much as I can because it doesn't look like a column density or a number density, but nevertheless, I even slip between some of these from time to time. I won't use N of Z or N of Z. I may use DNDZ. But it's the incidence of absorption lines, so it's how many absorption features per path length. That's why DNDZ makes some sense. L of Z, I have in mind a line density, the number of objects along a given line. So it's defined to be the number of lines detected on average in some redshift interval over some column density, which is straightforwardly determined from the integral of our frequency distribution. It's just our zeroth moment, and it's analogous, coming back to the analogy of the luminosity function of galaxies, it's analogous to the number density galaxies that you derive over some luminosity interval by just integrating the luminosity function. So, integrating one of the power laws that I just introduced, obviously you get another power law, and evaluate it over some h1 interval. You can ask the question then, what for a 5 angstrom patch of spectra in our data with a minimum h1 of 10 to the 12.75, how many lines would you expect? And a 5 angstrom patch works out to about a delta z of 0.004. So evaluating that, you find an average of 2.5 lines for a 5 angstrom swath, which is consistent roughly with what your eyeball picks out in the data. Here are actual evaluations from the spectra, from quasar data. Just focus for the moment on the binned evaluations, not the model fits, although you can see that straight lines do work well in this space. We have a steeply increasing incidence of absorption. That's what you saw at the start of the morning's lecture. When I scanned through the data as a function of redshift, you could see just by your eyeball that the incidence of lines rises sharply with redshift. And this is just a numerical description of what your eyeball was able to pick out straight away from the data. Here we also have a physical motivation for modeling the evolution and the number density, the incidence of absorption, this L of z or dndz. The cartoon. Consider a volume, a patch in the universe, a volume in the universe with, call them clouds, call them systems, call them what you will, structures that are giving rise to the absorption. So absorption, just call them lines if you will. But with 3D structure, so systems. Characterized by some physical number density, so objects per unit volume, and by some physical size. Maybe I'll give them a little more fuzziness, some size attribute to them. Okay. Run a random sight line through the box, and I think you'll agree that the incidence of objects that you'll hit along that path length is just proportional or equal to the number density times the cross section, right? Okay. So have that picture in mind. And I'm expressing it now in terms of r instead of s, but that's the physical proper length that as you travel through the universe, the number of absorbers you'd get per physical path length would be proportional to the number density of the sources and the size of the sources. Now introducing or bringing cosmology, the relationship between the physical delta of the proper path length and delta z is just given by c over the Hubble expansion times 1 plus z. If it was co-moving, it would just be c over h, as you probably know. So that means dndz, which is what we're after, is proportional to that, to n a h of z over 1 plus z. It turns out that the Hubble parameter, well, this is the Hubble parameter for a flat universe, omega k equals 0. It's omega m times 1 plus z cubed plus omega lambda at a redshift of 2 or 3, certainly by a redshift of 2 even. This term dominates over even omega lambda despite it having a higher value. So this can be approximated as 1 plus z to the 3/2 power. Fine. And in an expanding universe, we expect the number of sources per co-moving volume to remain roughly constant, not the number of sources per physical volume. Right? Expanding universe, expect number of sources per co-moving volume to remain roughly constant. So I replace the physical number density by the co-moving number density, nc. Altogether, then, you assert that dndz should be something like the co-moving number density, the size, the physical size, and some power 1 plus z. Here, 1 plus z to the 1/2. Okay, so we're motivated to consider dndz being proportional to 1 plus z to some power. Similarly, well, maybe not similarly, but in addition, the density of the universe is also increasing like 1 plus z to a power 1 plus z cubed, and insofar as the neutral fraction is the atomic fraction, the fraction of atomic hydrogen scales like the density, then that too may be some power 1 plus z. So we're motivated to fit the data, model the data with the 1 plus z power law, and indeed that's what's being shown in the figure here. And so it's plotted as a function of, it's a log-log plot, but the x-axis is a log of 1 plus z, and a straight line, a power law in 1 plus z is a good description of the data, at least over redshifts of 2 to 3 to 4. Great. And I put in the notes the actual parameterization that's shown there. 1 plus z to the 1 or even 4th power for the stronger absorption systems. You might ask, you should ask, how does this evolve over even greater swath of the universe? I'm plotting that now. Again, you saw by eyeball that the Lyman-alpha forest weakens, Lyman forest weakens as you go to lower redshift. Yet it actually does so in a fashion that's more shallow than what you would predict from an extrapolation of the power law that's been fitted to the higher redshift data. So this is the incidence of absorption in the local universe per delta z. And this is the extrapolation of what we just fitted from the high redshift data. And so indeed, there's a break in the evolution of the number density with redshift that we interpret as follows. Some cautionary tales, that's fine. We interpret this as being due to the fact, sorry, I don't need to say it in words. We interpret this being due to the fact that the UV background, the radiation field, which also affects the number density of atoms within the gas, has declined from a redshift of 2 to 1 as the quasar population disappears. Okay. And indeed, models that take into account the evolving UV background radiation more or less predict this, although there's some tension, and I think I'll reemphasize that again on Friday, between the prediction for this number density evolution and these observations. But to 0th order, that is a good description. The decrease in the UV background due to the disappearance of the quasar population more or less explains this change, rapid change in the evolution. Okay, we have now got a description of the shape in terms of column densities, the shape of the distribution function for B values, and the evolution in the normalization as a function of redshift. All right? And that's now which you would, if you will, a pretty complete description of empirical description of Lyman forest. Let me now apply this in a few ways, in a few fashions. One of them is we can now turn the problem around and build up mock spectra of the data. I think I'm going to leave that to the end in case, because I'm worried I will run out of time. But within the notebook, well, maybe I'll just flash through this. I've given you the recipe. Let's go back. Why not? If you wish to make up a mock Lyman-alpha forest for analysis of your own, or to, which is often what's usually done, or to test aspects of the opacity. Here's the approach. You have to choose, of course, some spectral range to analyze. Here, I'm going to go from 3,800 angstroms to, I think, a redshift, 3,800 angstroms to 2.5, to around 5,000, no, 6,000 angstroms. We need the frequency distribution, which we've just have derived, so f of n. And from that frequency distribution, over that redshift range, I draw the random number of lines proportional to our L of z times the delta z path. Actually, it's better to look at this in the notes. Let's come back to the notebook in a moment. Define the redshift path that you're interested in. That defines the number of lines that you expect to detect within the Lyman-alpha forest, n lines. Randomly draw a realization of n lines, randomly draw realizations of the column density from the frequency distribution, randomly draw B values from the distribution, randomly draw Z from the redshift evolution. Fine. That's what I've done so far in the notebook. So here's the random draws on the common density following our distribution function. Here's the random draws on the Doppler parameters following the distribution. I don't show the redshifts. Combining that all together with our astrophysics for the line profiles, you get an optical depth. You get an optical depth array, essentially, as a function of wavelength. So these are the optical depths of all these simulated lines within this Lyman-alpha forest. Okay. Some very highly saturated lines with optical depths well in excess of unity, some very weak lines down there on unity. From that, I can just make the perfect spectrum by taking the exponential of minus tau. There you go. There's a Mach Lyman-alpha forest. You would probably struggle to tell the difference between, well, except for the fact that it's perfect signal noise, you might have a struggle to tell the difference between that and real data. And then you can add in all the spectral characteristics you're interested in, resolution of the instrument, signal noise of the instrument, and I just kind of go through that there in a bit, and even an SED for the quasar. Fine. One example of using that distribution function. Let me now turn to effective opacities. The effective Lyman-alpha, the IGM as we've observed it and modeled it is highly stochastic, and would be very difficult to describe describe from the numerical simulations. As a result, one of the more powerful constraints cosmologically that we get from the IGM is the effective opacity. Here I'll start with Lyman-alpha. You'll see the full Lyman series in a few moments. And that's simply defined as the effective opacity is simply defined as the negative the natural log of the average flux that in the normalized spectrum of the Lyman-alpha forest. Sometimes also can be written as dA, where dA is just 1 minus the normalized flux. And the preferred approach to assessing this effective optical depth, tau effective alpha, is to take the average over many spectra and calculate the average flux observed. And from there, of course, it's just the negative the natural log to get the effective opacity. So, no, it's a slideshow. This is kind of nice to illustrate. So here's, these are individual. This is one individual spectrum from the Sloan Digital Sky Survey, Lyman-alpha forest region, at least particularly here on the right-hand side. One quasar spectrum, I think at a redshift of 4, maybe 3.5 in this case. And you can see again, as you have so far, the stochastic nature of the IGM. We're interested in this case not in the stochastic nature, but just the mean absorption associated with the IGM, okay, the average absorption at this epoch. And a pretty powerful approach here is to take 100, 150 spectra and average them together, and the stochasticity, of course, averages down. There's 2 spectra. Still quite a bit of stochasticity observed. 3 spectra, 9 spectra, 18 spectra, and 150 spectra. So by the time you've averaged together 150 realizations of this Lyman-alpha forest, and you could do that with the Mach data I showed you as well, maybe not surprisingly, you've averaged out that stochastic nature because the absorption from sightline to sightline is at random, essentially random redshifts. And it's this flux now that we're interested in. It's that average normalized flux that will give us this effective opacity. Again, to do that, I need to introduce a continuum. Here's the quasar composite continuum from that you've seen previously. And so it's this difference here between the intrinsic flux and the observed flux that is the estimate of the average effective opacity from Lyman-alpha. As I said, it's often written as dA. That's just the linear difference, but I prefer tau effective, which is the negative the natural log of the observed flux divided by the continuum flux. Okay. Any questions on that? So stack spectrum to get the empirically the average observed flux within the Lyman-alpha forest, compare that to our SED of the quasar to get an estimate of the effective opacity. Of course, that depends on the quasar continuum, which is somewhat uncertain. So this is also performed on high resolution data. Well, actually, it was originally performed. Let's come back. Let's skip that. So I've put in the notes how one may estimate from our frequency distribution, which we worked hard to derive, how you can estimate the effective opacity from our f of n. I think for sake of time, I'll just leave it in the notes. Empirically, or from observationally, let's show this at least. This is what we predict based on our frequency distribution for the contributions to this average Lyman-alpha opacity. The dominant signal comes from the absorption features, which have an opacity of order unity. That's probably not a surprise to you. The very weak lines, which we weren't well modeling, don't contribute very much. The strong lines, which are rare, also don't contribute very much. The damp Lyman-alpha systems, which have very broad absorption wings associated with them, do contribute a little bit, but are pretty minor players in the whole scheme of things. So we expect the signal, indeed, the signal is dominated by the lines with a tau 0 of order 1. The first best estimates on this, rather amusingly, were done with 3-meter data, even in the era of Keck. And the authors used an army of undergraduate students, I kid you not, to normalize the continua independently. They were locked in rooms with headphones and told not to speak to each other on how they were making an assessment of the quasar continuum, so that the lead authors could make an assessment of the systematic error associated with that process. That's folded into the analysis. Here are the data, the measurements for this dA quantity from those data, and modeled here, evolving from redshift 2 to 3, like a 1 plus z power law. The last slide. Forgot to show this last part here. I plot here the very last slide, which I didn't show, the averaged spectra ranging from 3.4 to 4.2 from the Sloan Digital Sky Survey. And as you see in the individual spectra, you see in the average spectra that the flux is decreasing with increasing redshift, that the average opacity is increasing as you go to higher and higher redshift. You see that in the average spectra. You see that in individual spectra, which is being plotted here. The next heroic effort was performed by Claude-André Fauché-Giguère, who took about 100 Echelle spectra, also fitted the data by hand within the Lyman-alpha forest to assess the effective opacity ranging from a 2 to 4. There are the main results. So a few tenths up to nearly unity as we hit a redshift of 4. And his best fit power law. And then the state of the art is to go back to these stacked spectra and perform a relative measurement within the Lyman-alpha forest. So you've seen this, I think, on day 2. Here again are 3 stacked spectra. The fact that the continua are so well behaved or so very similar outside of Lyman forest gives us faith that this relative measurement, how the average flux is decreasing with increasing redshift within the Lyman-alpha forest, must provide a very precise estimate of the average opacity, and indeed it does. You've seen already the slides. And here, now from the full glory of the Sloan Digital Sky Survey, is the average flux decreasing with increasing redshift out to about a redshift of 5, which is as far as you can really go with Sloan. And so combining the individual spectra from Kirkman and from Claude-André Fauché-Giguère with the relative measurement, this is purely a relative measurement from the Sloan Digital Sky Survey, we have a very precise description for how the effective opacity evolves from a redshift of 2 to 5, described by this rather ugly-looking power law plus offset term, which can then be applied directly to cosmological simulations, because within the simulations, this quantity is simply a reflection of the density field and the radiation field, okay? Which you could say is an unknown. Yeah, but let me pause there. So I'm now going to use these measurements for the average opacity to make estimates for the radiation field drawn within our cosmology. To do that, I introduce another description of Lyman-alpha forests, known as the Fluctuating Gun Peterson approximation. We've seen bits and pieces of this before as well. So, from the line profile, the lines at the line center of our Lyman-alpha line, the optical depth has equation 39, proportional again to n and f, and the width of the broadening of the line. Now consider a patch of the universe with some size delta r and some characteristic density, volume density nh1. From cosmology, we can relate that patch of the universe in physical size to redshift, as I just did previously. Okay. We recognize that the absorption occurs over the small redshift interval and relate that to our Doppler broadening. That is, all the absorption line, our Lyman-alpha absorption line has some characteristic width that we associate with the redshift. And we will introduce photonization balance now, actually, so that we can derive the radiation field. The ionization rate times the number density of hydrogen atoms just balances with the recombination rate, which Mark, I think, introduced, times the number density of electrons, the number density of protons. Putting that all together, we estimate the opacity in some patch of the universe will go like the recombination rate, the product of these densities, the inverse of the ionizing radiation field, and the inverse of the Hubble parameter. Okay. Now for the fluctuating aspect of this optical depth field. Let me introduce the overdensity delta, which relates the density locally within the universe to the mean density. So it's just the mean density times 1 plus delta. Delta greater than 0 is an overdense region, delta less than 0, an underdense region. And recognize that the number densities here then will provide us each with a 1 plus delta power. So you'll have the optical depth now going like 1 plus delta squared. Yeah? Does that say helium? I'm sorry, that's a typo. Hydrogen 2. I care a lot about helium 2, but not for this workshop. Sorry, I'll fix that. Yep, good catch. So, skipping over the ionization aspects of the number densities, but appreciating that the recombination coefficient goes like the temperature to the minus 0.7 power, as I think Mark described as well. And I may show this on Friday, I may not. The fact that the IGM is expected to follow a power law temperature density relationship, where the temperature now goes like this overdensity to some power law, beta. Numerical simulations predict beta of order 0.3. Putting all that together, here's the main takeaway point. We have a relationship now between the optical depth on small scales with the overdensity within that region and some complex redshift-dependent quantities that's hidden here in A, which I give in the notes, but are pretty messy looking. This is the fluctuating Gun Peterson approximation. Okay, so as we travel through the universe and go through regions of varying overdensity, you get a varying optical depth, and that gives rise to the fluctuations that we see within the IGM. Okay. If you have a cosmology, there's A of Z. Maybe look away for that. If you have a cosmology, then you can predict the distribution of these overdensities within that cosmology, and that can be related then that multiplied by our fluctuating Gun Peterson approximation, or E to the minus the fluctuating Gun Peterson approximation, gives us the average flux, which is what we've just measured from the spectroscopy. Okay, so this is what's been observed at high precision within from the data of the IGM And this is the formalism that relates the overdensities in our modern cosmology to average flux values in the universe. Within this A of z factor, as messy as it is, this is atomic data or in physical constants. This is the density of the universe, which we know very well, Hubble parameter, which is a function just of our cosmology, some ionization corrections, which are small. The mean temperature of the IGM, which is we just inferred was of order 10 to the 4 Kelvin, or a few 10 to the 4 Kelvin from the B values, and just a 1 plus Z factor. And lastly, the radiation field, which say would be an unknown. And so from having measured the effective optical depth at high precision, we can now make an estimate of the radiation ionization, the ionization rate due to the radiation field at high precision. And here's the estimation as a function of redshift. It's remarkably flat. Despite the fact that our average opacity increases so rapidly, that is explained by the cosmology, and one just needs a roughly flat radiation ionization rate to match the observations. Overplotted on this ionization rate is the ionization rate inferred from just quasars alone, bright quasars alone, and it led these authors, and still many other authors today, to argue that the radiation field must be dominated by galaxies as you head out to, say, redshift 3.5, redshift 4, as opposed to quasars, to match this ionization rate that we see derive from the average effective opacity that we get from the intergalactic medium. Questions on that? I know I went through that a bit fast. The derivation of the FB, all these derivations obviously in the notes, but the key takeaway point from the fluctuating gun Peterson approximation is we now have a way to link overdensity of the gas with the optical depth fluctuations that we see in the IGM, and we can apply that then to get the mean opacity and the mean, and compare that with the data to get an estimation of the radiation field. That was the estimation for Lyman-alpha. Of course, we can, from the data, now returning to the frequency distribution, make an estimation for all the Lyman series lines. Each one will contribute according to the frequency distribution. Okay, so adding up the various opacities, we see this curve. This is for a source at redshift 4. There's no opacity from the intergalactic medium beyond Lyman-alpha of the source, so 0 opacity here. Then immediately Lyman-alpha takes over and decreases, the opacity decreases as you head towards lower wavelength, lower redshift, due to the fact that the number density of lines is decreasing. And then here, Lyman beta opacity kicks in, again, then a decrease of each, gamma, delta, so on and so forth. Okay, and I'm not showing any opacity from the continuum, just the Lyman series opacity from redshift 4 source. That's the predictions from this frequency distribution. So I'm just integrating. That's it visually. We're just integrating. Not put it in. Yep. Okay. Over each of the Lyman series lines according to the frequency distribution which we've derived. That's the opacity. Of course, we see flux, so we need to consider the transmission, which is just e to the minus tau. And here's the transmission now that we would predict through that intergalactic medium as a function of wavelength. The flux is attenuated by about a factor of 2 to as much, even a bit more than that, or 50%, even a bit more than that as you go to the full Lyman series. And this has been applied, as I think you know, to, let's do this first. This is perhaps the most impressive plot of this lecture, at least to me. The black is the stacked spectrum I showed you, putting together 150 different observations of redshift 4 quasars. That's the average transmission, or the average recorded flux from the quasar. The red is the Telfer spectrum, so the composite spectrum actually derived at redshift of 1, with that mean transmission that I just showed you adopted on top of it. Okay, And you can see that with maybe the exception right here in the very bluest wavelengths, the description of the IGM that we've constructed is within a few percent an accurate description of the universe on average. I find that really actually quite stunning. Coming back to galaxies, that transmission is what led to the field of Lyman break galaxies. Okay, right. It attenuates the color for a Z of 4 galaxy for the transmission curve I just showed you. The magnitude in the G band is depressed by a full observer magnitude, not order of magnitude. And it was that insight that led the researchers, maybe 20 years ago now, to use this change in the color of the intrinsic color due to the IGM to search for signatures of redshift 3 and redshift 4 and now whatever, redshift 11 galaxies. Okay. This also leads to the attenuation that we've been seeing for the Lyman-alpha emitters. The depression, if you will, of the blue side of the Lyman-alpha line is due to the IGM, and it's this effective opacity as well. And that's probably the right place to start. Am I? Yeah, out of time. Okay. So to recap, I've given you the tools from the data to empirically describe the Lyman-alpha forest. That's this F of n formalism. We can use that to generate mock spectra of the Lyman-alpha forest. We can use that to predict the average opacity and transmission through the Lyman-alpha forest, the implications for the changing colors of our distant sources. We applied it to infer the effective opacity within the IGM from Lyman-alpha, which leads to a very precise determination of the ionization rate within our cosmology. And you'll see further applications in the next couple lectures as well. Thanks. Any questions on F of n? Yep.
Curious about connecting the effective Lyman-alpha opacity as a function of redshift to sort of observations of Lyman-alpha areas. You mentioned that it attenuates the blue side of the line. Should we expect to see anything else, or are there other ways to sort of figure out these fields?
I think you've heard hints of it, and you'll probably hear more. I'm sure you will hear more from Mark on what happens in the very high redshift universe, which I didn't probe or I didn't show here. Sticking to the less exciting redshift universe, redshift 5, certainly the asymmetry, the average asymmetry you should be measuring should be decreasing as you decrease in redshift. I'm not sure that's actually been quantified. And the IGM is not the only, of course, not the only thing giving rise to the line profile shape. So, at best it would be a statistical measurement, and probably one that wouldn't be so clean to measure. But dinner, or time before dinner.
No more announcement? Nope. Yeah,
Good.
enough.
All right. Thanks.